So I'm going to work through the problems on your review sheet for the test in case we don't have class on Monday. So the review sheet is on Angel, and I've adjusted it since I adjusted it this morning, Friday morning. So it may be different than the one you downloaded. If you downloaded it earlier, you may want to take a look. I just put a few more topics on for us to go over. So the first section of the review sheet is to make sure that you can find the derivative by the definition. So I have three different problems that you have to find the derivative by the definition for. And so if you have to do that, then you need to remember that the definition says the limit as h approaches 0 on the function evaluated at x plus h minus the function evaluated at x all over h. And I'm going to check and make sure that that's coming up on here. Just got to make sure I have the camera adjusted correctly. Okay. So for the first one, for 1a, if the function is 3 over 2x minus 3, then you would want to take the limit as h goes to 0 on 3 over 2 times the quantity x plus h minus 3, because that's the function evaluated at x plus h. You're plugging x plus h in where the x was. And you have to double it before you take away 3. Minus the function as it is all over h. And in this type of problem where it's a fraction, the strategy is to get a common denominator. So we're going to take the limit as h goes to 0, and our common denominator is going to be the product of the two denominators that we have. The 2 parentheses x minus 3 and the 2x minus 3. And then the numerator of that, when we put these two fractions together, will be 3 times 2x minus 3 minus 3 times 2x plus h, quantity, minus 3. So that's my numerator when I get a common denominator. Then I have to simplify. So one step in simplifying is to pull my two denominators together. So I have my h and my 2 quantity x plus h minus 3 and my 2x minus 3. And then I've got to distribute and simplify up here. So I'm going to have 6x minus 9 minus whatever this is. So I'm going to take a minute to figure out what this is. So this is 2x plus 2h minus 3 if I distribute through these parentheses. And then I got to distribute the 3 through. So it's minus 6x minus 6h plus 9 when I distribute the 3 through and the negative. And so my 6x and my negative 6x add to 0, my 9 and my negative 9 add to 0, and I'm left with the limit as h goes to 0 on negative 6h over h times all this stuff, my common denominator. I can divide my h's out, and once I do that, I can send the other h to 0, which is taking the limit. So I end up with negative 6 over 2x minus 3 quantity squared. And that is my derivative for this particular function. So on 1b, the difference is that I'm going to do the limit as h goes to 0, but my function is the square root of 3x minus 4. So when I evaluate that function at x plus h, it'll be the square root of 3x plus h minus 4. And the function itself is the square root of 3x minus 4. And this is all over h. So I don't have a common denominator issue this time. I need to use the conjugate. So the conjugate is the two radicals that you have in the numerator, but with addition instead of subtraction. And we're going to make it the number 1 by putting it on top of it itself. So the square root of 3x plus h minus 4 plus the square root of 3x minus 4 over itself. And so what I end up with then is the limit as h goes to 0 on, when I multiply the radicals together, I end up with what's underneath. So I'm going to get 3x plus h minus 4 minus 3x minus 4 all over h, and then the conjugate, square root of 3x plus h minus 4 plus the square root of 3x minus 4. So what that gives me then is the limit as h goes to 0 on, this is 3x plus 3h when I distribute. Well, my 3x and my negative 3x will go to 0, and my negative 4 and my minus negative 4 will go to 0. So the only thing up top is 3h, and on the bottom I have my h and my conjugate. So at this point, I'm going to divide my h's out. I'm going to send the other h to 0. And my final answer will be 3 over 3x minus 4 under a radical plus itself. So I'm going to write that as 2 times 3x minus 4. And that's my final answer. So you end up with, if you checked it with the rules that you have, you should find out you get the same thing. The last one by definition is doing that same thing on the function 2x minus 3 squared. So we're going to do the limit as h goes to 0 on 2 times x plus h minus 3 squared and minus 2x minus 3 squared all over h. And in this case, the way you have to do it is with expansion. You have to multiply all this stuff out. So we're going to do the limit as h goes to 0. I know how to expand out 2x minus 3. It's 4x squared minus 12x plus 9. Just FOIL it. But the other one I need to think about a little bit. So if I deal with the parentheses inside, 2x plus 2h minus 3, and I need to multiply it by itself, to me the fastest way to do it is 2x times the entire thing up here, so that's 4x squared plus 4xh minus 6x. Then I'll multiply 2h through, so I'll get another 4xh plus 2h through. 4h squared minus 6h, and then I'll multiply negative 3 through. So I get a negative 6x minus 6h plus 9. And when I put all that together, I'm going to have 4x squared plus 8xh minus 12x plus 4h squared minus 6x plus 9, which is a big mess, but I got to fit that all here. So 4x squared plus 8xh minus 12x plus 4h squared minus 6h plus 9. The good news is when I distribute my negative through, the 4x squared will go to 0, the 12x will go to 0, and the 9 will go to 0. So I'll be left with 8xh plus 4h squared minus 6h, and that's it. So at that point, I can divide everything through by h and get 8x plus 4h minus 6, and then I can send h to 0 and get 8x minus 6. So there's my derivative, by definition. Okay, and we've done that many, many times, so that was just one more time to see it. The next section that I want to talk about is section number 2. And section number 2 is the difference between the average rate of change and the instantaneous rate of change. So instantaneous rate of change is a derivative, and average rate of change is f of b minus f of a all over b minus a. So that's something you need to know. And then we're going to do it on this particular function, which is a cost function. So my cost function is the variable cost, which is 3.6. Oh, I'm sorry, no, sorry, my cost function is a little more complicated. It's not just a fixed cost plus a variable cost. It's got more to it. So there's my cost function. And to find the average rate of change, which is A, I want to do f of b minus f of a over b minus a, and then I got to look back and say, what are a and b? So they said from 250 to 300. So that's my a and that's my b in this problem. So I want to evaluate the cost function at 300 minus evaluate the cost function at 250 all over 300 minus 250. Now to evaluate the function, I would actually need a calculator, and unfortunately I didn't bring one in the room, but it would take 3.6 times the square root of 300 minus plus 500, sorry. Don't really need to say plus 500, you'll see why in a minute, but that is the cost for 300 units, minus 3.6 times the square root of 250 plus 500, all over 50, which is 300 minus 250. The reason I didn't really need the 500 is they're going to subtract away. But I would need to take on my calculator 3.6 times the square root of 300 minus 3.6 times the square root of 250 and figure out what that is and divide it by 50. So you will get a decimal answer for that if you plug it into your calculator. But for B, for the instantaneous rate of change, you would need to take the derivative, and they said the instantaneous rate of change for 250 units. So that means when x is 250. That's, x is always our number of units. So if I want the instantaneous rate of change, I need to take the derivative of the cost function. So to think about the cost function as 3.6 x to the 1/2 plus 500 is the best way to think about it if I'm going to take its derivative. So I'll move the 1/2 down and make it 1.8 x to the negative 1/2. The derivative of 500 is 0. So the derivative of that, I don't have to worry about that. So now C prime of 250 is 1.8 times 250 to the negative 1/2. Again, that's a calculator problem. You could evaluate it and give me an answer. This is the instantaneous rate of change for 250 units. Meaning, if I asked you what did you just find? You found the rate of change in cost with respect to units. In other words, if I make the 251st unit it will cost, whatever this number is, when it's calculated, dollars. It'll cost that many dollars. And again, I don't have a calculator to actually calculate it out, but whatever that is, that many dollars to make. It's the marginal cost, the cost to make the next unit. So that's section number 2, difference between average rate of change and instantaneous. Section number 3, there were a bunch of derivatives, and I said find the given derivative. So second derivative here, first derivative here, dy dx is the first derivative, first, second, first. Just a bunch of different functions that you need to be able to take the derivative of. So you can fast forward to any of them that you think you might have an issue on. I'm just going to go through them one at a time. So the first one that I'm going to tackle is 4a, which is f of x equals 4 times x squared minus 3 to the 5/2. And I want the second derivative. So I'm going to get the first derivative using the general power rule. This is a constant multiple 4. This is a function of x raised to the power. So I'm going to use the general power rule. And I'm going to leave the 4 where it is because it's a constant multiple. I'm going to bring the 5/2 down, so it's going to multiply by that 4. I'm going to leave the function just as it is, but drop its degree to 3/2. And then I have to multiply by the derivative of the function, which is 2x. So there's my general power rule, and I end up with having a 4 and a 5/2 and a 2 that I need to multiply up. To simplify this a little bit, so that's 20 divided by 2 times another 2. So I'm guessing that is 20, 40 divided by 2, 20 in the end. Yeah, that wasn't too hard. And then there's an x here that I'm just going to put first, and then there's an x squared minus 3 to the 3/2. So now I got to take the second derivative. This is going to be harder because I need the product rule. And in the midst of the product rule, I'm going to also have to deal with that power, just like I did previously with the general power rule. But the difference between this derivative that I found, and I'm trying to take the derivative of again, and the original function, I didn't need the product rule on the original function, but I do now. So when I go to take the second derivative, I'm going to leave the 20 like a constant multiple. And I am going to then think about, this is my first function, x, and this is my second function, x squared minus 3 to the 3/2. I'm going to leave the first function alone, and I'm going to take the derivative of the second by pulling the 3/2 down, leaving the inner function alone, dropping the degree to 1/2, and multiplying by the derivative of the inside. And I did that faster this time because I've already done it once, so it's easier. Plus, now I'll leave the second function alone and multiply it by the derivative of the first, which is really easy because it's 1. So there's my second derivative, and I need to simplify it. And you know you need to simplify it when you use the product rule together with the general power rule, because you're going to have this common factor to pull out. So the final step would be to pull out x squared minus 3 to the 1/2 and then write what's left. So my 3/2 times my 2, that can become a 3. And I got an x squared. Plus, I have the other factor of this, that x squared minus 3. And that leaves me with, finally, 20 x squared minus 3 to the 1/2. 4x squared minus 3 is my other factor for my second derivative. 4b. I need the first derivative of this thing. And I have 2 square root of x all over 3x, and actually that 2 is a negative. So that's what I'm taking the derivative of. So this is the type of problem where the denominator is a monomial, and that's my clue that I need to rewrite this function before I take its derivative. I need to know what the coefficient is, which is 2/3, negative. And I need to know what the power is on x. And the way I figure that out is the power on this is 1/2, the power on this is 1, I subtract them and I get negative 1/2. So thinking about it as negative 2/3 x to the negative 1/2 is the best way to go, because for a first derivative, all I need to do is bring my negative 1/2 down and multiply and get 2/6 or 1/3, and then drop my degree from negative 1/2 down to negative 3/2. And that gives me 1/3x to the 3/2 when I rewrite it as my first derivative. For 4c, I need the first derivative called dy dx. And the way the function's written, I should realize I'm going to have to use implicit differentiation, because it's not written y equals. I can't make it say y equals without using a plus or minus. So I'm going to have to go left to right and just take a derivative of everything I encounter with respect to x. So the derivative of x with respect to x is 1. I'm adding on now the derivative of this thing, which requires the product rule, because it is a function, which is x, times a function of x, y squared. And anytime you multiply two functions together and you want to take their derivative, you need the product rule. So I'm going to leave my first function alone as x and take the derivative of my second. I need the general power rule here. I'm going to pull the 2 down, I'm going to drop the degree on y to the first, and I'm going to multiply by the derivative of y with respect to x, which is dy dx. Plus, now I'm going to leave the second function alone, y squared, times the derivative of x, which is 1. And then I'm going to take the derivative of 4, which is 0 no matter what. So, I have 3 things on the left here connected by addition, so 3 terms. And I want to leave the one with the dy dx on the left. I'm going to rewrite x times 2y as 2xy. And that's times dy dx. But the other 2 terms that don't have a dy dx attached to them, I'm going to send them to the other side. And over there, the 1 is negative 1, and the y squared is negative y squared. And my last step then is to divide by this thing that's being multiplied by dy dx. Negative 1 minus y squared all over 2xy is my derivative. Implicitly, and that's how I end up with dy dx. 3D. I've been calling these 4 and they're 3. 3D is the derivative of the function x cubed square root of x. And I only want the first derivative. Well, you may think, oh, I need the product rule because x cubed is a function and square root of x is a function, but you don't. What you need to do is multiply these two by adding the exponents. And that's a way you can get around the product rule. You don't need the product rule for this problem. If you rewrite your function as x cubed times x to the 1/2, and you add the exponents, you'll see it's the same as x to the 7/2. And so the derivative of that function is 7/2 x to the 5/2. That simple. If you use the product rule, you'll end up with the same thing, but it'll be a lot longer. So you want to think about 3D the same way we thought about, this is 3B. You want to put them together in your mind. If I'm dividing, I want to subtract my exponents and figure out what the function looks like. If I'm multiplying, I want to add the exponents and think about what the function looks like before I take the derivative. 3e was f of x equals a quotient. So x squared minus 16 on top, 2x plus 8 on the bottom. And I want the second derivative. So that should strike fear because, holy cow, do I have to do the quotient rule and then do it again? But if you think carefully, you do not. Because even though this is not a monomial on the bottom, if you understand that this is 2 times x plus 4, and you understand that x squared minus 16 is x plus 4, x minus 4 in another life, another way to think about it, then you can be smart and rewrite your function before you go and take the derivative and simplify it. So the x plus 4's can divide out. And this function really is x minus 4 over 2, as long as x is not negative 4. If x were negative 4, then you can't say that. But we'll make this little caveat. And then you say, wow, this is going to be the easiest problem on the test, because that means my function really is a half of x minus 4. And the derivative of my function is a half of 1, or a half, and the second derivative of my function is 0. It's really a linear function whose derivative is the slope of that line, the second derivative is 0. So whenever you have a quotient, before you jump to the quotient rule, see if there's any simplifying you can do. And that's just an algebra habit you want to be in. 3f. Now this one is the bugger. This one is not going to be very simple. So let's take a look at it. And if we can do this, we can do anything. So what I have is this function x squared minus 5 over the square root of x minus 2, and it's all to the 1/2 power. And I just want the first derivative. So this function was under a square root, and I decided to take that square root and rewrite it as a power, because I know that's what I always do if I'm trying to take a derivative. So I think I'm going to do that on the square root down here also. I'm just going to think about it as x to the 1/2. And now I've got to think through what levels are there to this function if I'm going to take its derivative. And the outermost of the functions is this 1/2 power. That's like the last level. If I were going to plug in for x, I do a lot of stuff, but the last thing I do is take the 1/2 power. So that's where I've got to start with my derivative. Inside, so like an inner function is a quotient. X squared minus 5 over x to the 1/2 minus 2. So I got to start with my power, and then I'll go to my quotient. And when I do my quotient, I'll have to think about, the derivative of each of these independently of each other. So my derivative will look like this. Pull the 1/2 down. Don't change this function, but drop the degree to negative 1/2. Now I need to multiply on the derivative of this function, and that's when I need the quotient rule. So I'm going to square the denominator, start with the denominator. The derivative of the numerator is 2x minus the numerator times the derivative of the denominator, which is 1/2 x to the negative 1/2. It's a big problem, but in it I've done the general power rule and the quotient rule. So I need to simplify a little bit just because I see negative exponents. And I'm trying to think about the best way to do that. I guess the best way to deal with this one is to just flip everything over. This negative 1/2 power, this can flip over, and now it'll be the positive 1/2 power. So that was easy. Flip the base and it'll be a positive power. This one's not quite so easy. So I think what I'm going to do on this one is, there's a lot of different things I could do, but I think I'm going to do what we talked about in class on Friday, which is keep everybody the same. Think about this x squared minus 5 as over 2x to the 1/2, so I'm going to use the 1/2 and the negative power to rewrite it as a fraction. And then I'll do what we learned on Friday, which is multiply everything in the complex fraction by the denominator. And the denominator here is 2x to the 1/2. So I'm going to multiply this piece by 2x to the 1/2, and it's going to become 4x to the 3/2. I'm going to multiply this one by 2x to the 1/2, which is going to make it x squared minus 5. And then I'm going to multiply the denominator by 2x to the 1/2, which is just going to stick a 2x to the 1/2 down there. So this would be could be your final answer. You could also distribute through and simplify a little bit, but I'm not going to go that far. Don't leave negative exponents. That's the rule, and I didn't leave any. All right, so moving on to section 4. Section 4 said, find the equation of the tangent line to the function at the given point. So I've got to think through before I jump into any problems. The equation of the tangent line. So first thing in my mind is I need the point slope form because I want an equation of the line. So I know that. And I could even write y minus 4 and x minus 1 if I want. I know what the point is. But the question is, how do I get the slope? And the answer to that question is with the derivative. So this slope is going to be dy dx when x is 1 and y is 4. So having thought that through, my goal right now, my mission is to find dy dx and then plug 1 and 4 in. So we talked about that you don't think about the square root of xy as the square root of xy. You think about it as x to the 1/2 and y to the 1/2. So I'm going to do that. And then it's minus y equals negative 2. And again, my point is 1/4. So I'm going to take the derivative implicitly, which means I'm going to use the product rule here. X to the 1/2 times 1/2 y to the negative 1/2 dy dx, because I'm taking the derivative of y, and that's dy dx, plus now I'll leave y to the 1/2 alone. Derivative of x to the 1/2 is 1/2 x to the negative 1/2. So I use the product rule, got that. Minus the derivative of y is dy dx, and the derivative of negative 2 is 0. So now I have a choice. I can go ahead right now and plug in for x and y. And I think that's a good idea, because otherwise I'm going to have to factor a dy dx out and move this to the other side, and it's going to be a big mess of algebra. But if I have a point and I know what x and y are, I'm just going to plug them in right now. So x to the 1/2 is 1 to the 1/2, which is 1. Y to the negative 1/2 is 4 to the negative 1/2. dy dx. Y to the 1/2 is 4 to the 1/2. 1/2 x to the negative 1/2. If I plug 1 in, that's still 1. dy dx. So now I can plug this into my calculator if I have to, although I know that this says flip it over and take its square root. So I get 1 times a half times another 1/2. That's what 4 to the negative 1/2 is. dy dx. Plus, this is the square root of 4, so that's 2 times 1 minus dy dx. So in other words, it's 1/4 dy dx plus 2 minus dy dx. That equals 0. And I can move the 2 to the other side, and I can factor the dy dx out of what's on the left, and I get 1/4 minus 1. So dy dx is -2 over -3/4, or -2 times -4/3, or I can't multiply, 8/3. That's my slope. So it's much easier to do this problem if you plug the numbers in rather than solving it in terms of x and y. So my equation is y minus 4 equals 8/3 x minus 1. And that's how you handle the equation of a tangent line. You use dy dx to get the slope and plug it in. Number 5 is the diver problem. So you need to know for the diver problem how to write a position, velocity, and acceleration function. And the position function is -16t squared always, plus initial velocity, which in number 5 is given to be 2 times t, plus initial height, which in number 5 is given to be 20. So problem number 5 gives you everything you need to know, the height and the initial velocity. That's all you need to know to write a position function. So -16t squared plus 2t plus 20. Velocity comes from the derivative of position, -32t plus 2. Acceleration comes from the second derivative of position or the first derivative of velocity, but it's always a constant, -32. Next, I was asked, when does he reach his highest point and what is it? Highest point highest point is when velocity is 0. Or you could use -b over 2a if you prefer. So -32t plus 2 is 0, -32t is -2. In 1/16 of a second, he reaches his highest point. So I'm going to then answer the second part of that question, which says, what is the highest height he reaches? So in order to figure that out, you got to plug that 1/16 of a second into your position function. And it looks like if you calculate that out, you get 20 and 1/16, because this is -1/16 and this is +2/16, so that many feet high. So set velocity equal to 0 or use -b over 2a. Either way, you'll get 1/16. Last part of 5 is when does he hit the water? 5c. When does he hit the water? So that's when position equals 0. He hits the water. And so you need to set -16t squared plus 2t plus 20 equal to 0. I'm going to just divide by 2 to make my number smaller. Divide both sides by 2. And then at this point, I either have to be really good at factoring and see if this factors, or I'm going to use the quadratic formula. The opposite of b plus or minus b squared minus 4ac all over 2a. And calculate that out. -1 plus or minus the square root of 321 all over -16. Again, I don't have my calculator, so I need to plug it in and figure it out. But I'm really only going to take the -1 minus the square root of 321 all over 16, negative 16, because that'll be my positive answer. So whatever that is, that's my answer. Or you can use your graphing calculator to figure that out if you know how to do that. You don't have to do the quadratic formula. Number 6 says, know the formulas in general. So for example, if I said that I had a function that was the quotient of two other functions, and then I told you that I wanted you to find f prime of 7, this is a general question like on the last quiz you took, you'd have to know that the derivative of this is square the denominator, start with the denominator, times the derivative of the numerator minus numerator times the derivative of the denominator. I mean, that's just something you need to know in general. Because I'm going to give you all the values you need, but you have to know where to plug them in. So I'll give you f of 7, f prime of 7, g of 7, g prime of 7. That'll be given somewhere on your page. So I'll just say there are 1, 2, 3, and 4. But you need to know where they go. So it would be h prime of 7 would be g of 7, which is 3, times f prime of 7, which is 2, minus f of 7, which is 1, times g prime of 7, which is 4, all over g of 7 squared. And so 6 minus 4 over 9, 2/9. Those problems are very simple if you know the rules in general. So you have to know them all. All the ones I gave on your review sheet, you need to know. The product rule, the quotient rule, the general power rule, and the chain rule. Know those inside and out for a question like this. Number 7. There are two types of demand functions you have to be able to write. The first one, a linear one, you had on your last quiz. The second one is the inversely proportional one, which we did on a worksheet. Those are the two demand functions you're responsible for. So if we look at 7a, and I'm going to try to do it right underneath so I can use the information. For 7a, we've got, I open a business and I discover that if I price my product at $4, I can sell $2,000. You need to see that as a point on the demand function. Units, comma, price. And for every 25 cents I drop the price, so if I drop the price to $3.75, I sell 100 more units. So this would be 2,100. You need to come up with those 2 points, and the words for every tell you this is linear. And those 2 points help you come up with the demand function. The slope, 4 minus 3.75 all over 2,000 minus 2,100, 0.25 over negative 100, negative 1 over 400. So there's my slope. And I'm going to write y minus a y value equals the slope times x minus the x value. And y is p. Y represents the price every time, because when you're doing a demand function, you graph your p on the y-axis and your x, which is units, on the right. So if I need to come up with a revenue function from here, I want to solve this for p, which means I distribute through, and I'd have negative 1 over 400x, and then I distribute here and get 5, and I'd add the 4 to it, and it would be 9. So there's my demand function, a linear demand function. I did that quickly because we've done that many times and it was on your quiz. 7B, inversely proportional, a little different. A business discovered the demand, which is X, for their product was inversely proportional to the square of the price. So the way we set that up is X equals some constant over P squared. The demand is inversely proportional, so the P is in the bottom, to the square of the price, so the P is squared. But I got to figure out what my constant of proportionality is before I can finish this problem. That's from the when statement. When the price was set at $20, so when P was 20, 40,000 units were sold. That helps me figure out what K is. K is 40,000 times 400 when I square 20. Because I have to make this 400, multiply both sides by 400. So K is 16 with 1, 2, 3, 4, 5, 6 zeros. 16 million. So X equals 16 million all over P squared. That is a demand function. It's a function relating units and price. However, again, if I need a revenue function, if my next goal is revenue, then I want to make this say P equals, because that's what I plug into revenue, P. So we've talked a lot about how to do this. You switch on the diagonal. So P squared is 16 million over X. And then you take the square root. The square root of 16 million is 4,000. And the square root of X is the square root of X. Either of these are demand functions. They're both demand functions. But this is the one that can get me to revenue. Because if I need a revenue function, all I would do is take this demand times X. That's how I get revenue. So I multiply them together and get 4,000 square root of X. Because X divided by the square root of X is the square root of X. So it's important to understand demand functions can be written X equals or P equals. But if you want to get to revenue, you need to get it to P equals. All right, next problem is number 8. And it ties into what we just said. If you're given a demand function and it says P equals, then it's really easy to write a revenue function. So if they tell you P is 5 minus 0.001x, that's your demand function. To get a revenue function, all you got to do is take that demand times x. It's P times x for revenue. And so your revenue function would be 5x minus 0.001x squared. If they then also give you a cost function, which is a fixed cost plus a unit cost, and you need a profit function, all you got to do is take your revenue minus the cost. So you take your revenue function minus your fixed cost, which was 37, minus your unit cost, which was 1.5x. You want to simplify that to negative 0.001x squared plus 3.5x when you combine your x terms minus 35. But that is your profit function, revenue minus cost. So those are two functions you need to know. Revenue is x times p or p times x. Profit is revenue minus cost. Next thing I said is write the marginal profit function. Well, you need to know that marginal profit means the derivative of profit. So in this case, it'd be negative 0.002x plus 3.5. And if I asked you what marginal profit was, it's the profit for the next unit that you sell. So if I plugged 100 in here, I find the profit for the 101st unit. That's what marginal profit is. It's the extra profit for that next unit. And then finally, I said number 9, understand the graphical idea of what a tangent to a curve means. So what I mean by that is, if you have a graph of a function, I want you to have an idea in your mind of what the tangent looks like. So at this point in your curve, you should have an idea in your mind that the derivative is measuring that slope of that tangent, and that means the derivative should be 0, because the slope of the tangent there is 0. You should have an idea that if I'm talking about here on the curve, the slope of the tangent has a positive slope to it. So you should know that the derivative would be greater than 0 there. And right here on the curve, the slope of the tangent line, which is sort of approximating the slope of the curve there, is negative. So the derivative would be negative. And there might be places on the curve, like here, where the derivative is actually, the slope of the tangent line is actually vertical, so the derivative is undefined, because your tangent lines get steeper and steeper and steeper, and they go vertical there. So you want to have an idea of what this tangent is representing when you're finding it. And the derivative is always the rule for the slope of that tangent line. So when you find ui dx, or f prime, or whatever you want to call it, you're finding the rule for the slope of the tangent line to that curve. So that's my review for the test. If you have questions, make sure that you call me or email me. Happy to answer them over the weekend or on Monday. But otherwise, I will see you the next day that we have class will be the test, unless we happen to have class on Monday, and then we'll be doing this all over again.